Welcome back to our lecture series on the history of Indian science. In our previous session, we explored how scientific ideas change and develop over time, focusing specifically on the evolution of mathematical and astronomical knowledge in the Indian tradition. We examined how simplification drives innovation, how unexplained observations stimulate new theories, and how practical needs shape theoretical development. Today, we're going to broaden our perspective. We'll explore a fascinating phenomenon in the history of science: parallel development. Throughout history, different civilizations have often worked simultaneously on similar scientific problems, sometimes developing comparable solutions despite having little or no direct contact with each other. This parallel development raises intriguing questions about the nature of scientific knowledge and the relationship between cultural context and scientific discovery. Let's begin by considering what we mean by parallel development. Imagine two mathematicians working in different parts of the world, one in Kerala, India, and one in Renaissance Italy. Both are trying to find better ways to approximate trigonometric functions. Neither knows about the other's work. Yet, remarkably, they might develop similar methods, using different notations and expressing their ideas in different languages, but arriving at mathematically equivalent approaches. This kind of parallel innovation has occurred repeatedly throughout the history of science. What factors lead to such parallel developments? Several key elements come into play. First, similar problems often demand solutions. Across different civilizations, people needed to measure land, track celestial movements, create calendars, navigate ships, and conduct commerce. These common challenges naturally led to mathematical and astronomical innovations in various cultures. Second, there's the matter of available knowledge. Different civilizations worked with the mathematical and observational tools available to them. These starting points influenced the paths they took toward new discoveries. Sometimes, similar starting points led to similar developments. Other times, different starting points led to novel approaches to common problems. Third, we must consider communication networks or their absence. In some cases, knowledge diffused along trade routes or through translated texts. In other cases, civilizations developed scientific knowledge in relative isolation from each other. Understanding these patterns of communication, or lack thereof, helps us interpret instances of parallel development. As we explore parallel scientific thinking today, we'll focus on major centers of mathematical and astronomical innovation across several civilizations: India, Greece, China, the Islamic world, and even Mesoamerica. Each of these regions developed sophisticated mathematical and astronomical traditions, often during overlapping time periods. The timeframes of these developments are worth noting. While Greek mathematical achievements flourished particularly from around 600 BCE to 300 CE, Indian mathematics and astronomy saw major developments from the early centuries CE through the medieval period. Chinese mathematical texts date back to at least 200 BCE, with significant developments continuing for many centuries. In the Islamic world, mathematical and astronomical work flourished especially from the 8th through 14th centuries CE. Mesoamerican calendrical and astronomical systems were well developed by the first millennium CE. These overlapping timeframes created numerous opportunities for parallel development. Sometimes these parallel developments occurred with little or no awareness between traditions. In other cases, there was some exchange of ideas, but each tradition developed those ideas in distinctive ways, shaped by their own cultural and intellectual frameworks. What makes parallel scientific development so fascinating is that it reveals something profound about the nature of mathematical and astronomical knowledge. When different cultures independently develop similar concepts or techniques, it suggests that these mathematical truths have a certain universality. At the same time, the different expressions and applications of these concepts highlight the influence of cultural context on scientific thinking. Today's exploration won't just be about cataloging similarities and differences between traditions. Instead, we'll examine what these parallel developments tell us about the scientific process itself. How do different philosophical foundations shape mathematical approaches? How do cultural needs and values influence which problems scientists prioritize? How do different modes of expression, different notations, terminology, and conceptual frameworks affect the development of scientific ideas? By the end of this lecture, you'll have a richer understanding of how scientific thinking develops in different cultural contexts, and you'll be better equipped to appreciate both the universality and the diversity of mathematical and astronomical knowledge across civilizations. This comparative perspective will help us move beyond simplistic questions of who discovered what first to a deeper appreciation of the complex, interconnected, yet culturally distinctive paths of scientific development. Now, let's begin our exploration of how different civilizations approached similar mathematical and astronomical problems, starting with a comparison of the philosophical foundations that shaped their approaches.